Study and comparative analysis of effect of SiC and Graphite Composite on Aluminiun using RSM methodology. Abstract. In this present work, systematic study has been conducted to investigate the wear phenomenon by adding micron-size silicon carbide and graphite particles into Al6061 base. Al6061 compound was taken as the base lattice to which SiC and graphite particulates were utilized as fortifications. 3 weight %, 6 weight %, and 9 weight % of SiC and 3 weight %, 6 weight %, and 9 weight % of graphite were introduced to the base framework. The wear behavior analysis, which uncovered the uniform appropriation of SiC and graphite content in the Al matrix. Pin-on-disc equipment was utilized to assess the volumetric wear loss of arranged samples, in which EN32 steel disc was utilized as the counterface. The outcomes uncovered that the volumetric wear misfortune was expanded with increment in applied load, disc speed, and sliding distance for every one of the specimens. The outcomes additionally showed that the volumetric wear loss of the Al6061 to 9% SiC 9% graphite composite was smaller than the Al6061 to 9% SiC 9% graphite. The worn-out surfaces were portrayed by RSM analysis. 1. Introduction 1.1 Metal Matrix Composite. The metal matrix composites, MMCs, are very attractive materials for several applications. For many researchers, the term MMCs is often equated with the term light metal matrix composites. Substantial progress in the development of light metal matrix composites has been achieved in recent decades, so that they could be introduced into the most important applications. Aluminum matrix composites, AMCs, are the competent material in the industrial world. Efforts have been made to develop aluminium metal matrix composites in recent years due to their low density, high strength, and superior creep resistance, and have great potential in automotive and aerospace applications. Aluminium, Al, is the second most widely used metal in the world today after iron. It has a low density, 2.7 G/cc, superior malleability, excellent corrosion resistance, good thermal conductivity, 237 W/mK, very low electrical resistivity, 2.65*10-8 ohm, and good formability. Its Young's modulus is 70 GPa and its Vickers hardness is 60 to 70 Vhn. Al has a melting point of 660.32 degrees Celsius, and at high temperatures, the strength of Al decreases. However, the demand for Al and its alloys having a much higher strength is increasing. 3. Al matrix composites, AMCs, have been widely used in automobile and aerospace industries due to their excellent physical and mechanical properties. To overcome these shortcomings and to meet the ever-increasing demand of modern-day technology, composites are one of the most promising materials. 3. 1.2 Alloy, Aluminium 6061. 6061, UNS designation A96061, is a precipitation-hardened aluminum alloy containing magnesium and silicon as its major alloying elements. Originally called Alloy 61S, it was developed in 1935. It has good mechanical properties, exhibits good weldability, and is very commonly extruded, second in popularity only to 6063. It is one of the most common alloys of aluminum for general-purpose use. It is commonly available in pre-tempered grades such as 6061O, annealed, tempered grades such as 6061T6, solutionized and artificially aged, and 6061T651, solutionized, stress-relieved, stretched, and artificially aged. Silicon carbide, SiC, also known as carborundum semiconductor, is a containing silicon and carbon. It occurs in nature as the extremely rare mineral moissanite. Synthetic SiC powder has been mass-produced since 1893 for use as an abrasive. Grains of silicon carbide can be bonded together by sintering to form very hard ceramics that are widely used in applications requiring high endurance, such as car brakes, car clutches, and ceramic plates in bulletproof vests. Electronic applications of silicon carbide such as light-emitting diodes, LEDs, and detectors in early radios were first demonstrated around 1907. SiC is used in semiconductor electronics devices that operate at high temperatures or high voltages, or both. Large single crystals of silicon carbide can be grown by the Lely method, and they can be cut into gems known as synthetic moissanite. Aluminum-silicon alloys exhibit several features of tribological behavior which are similar to those of aluminum-based MMCs. Zoomgar, 1987, has summarized the effect of silicon content in Al-Si alloys in dry sliding wear. Wear resistance is improved in mild wear conditions if the silicon content in Al-Si alloys is increased. Andrews, 1985, measured mild wear of several hypereutectic LSI pins with approximately the same matrix composition sliding against an M2 steel disc. The wear resistance of each alloy increased with primary silicon content up to a maximum at 17% Si, total matrix and primary Si content of 26%. A transition load at which wear rates changed from mild to severe was also identified for different silicon contents and sliding speeds. Based on data from Andrews. 1985, a load velocity diagram is plotted in that indicates the beneficial effect of silicon content on resistance to severe wear. The onset of severe wear occurred at a characteristic transition load, at which a small quantity of aluminum adhered to the steel disc. This transferred deposit grew in size and initiated gross plastic deformation and fracture of the aluminum alloy pin as the test progressed. Material removal occurred by subsurface crack propagation in a composite transfer layer of aluminum and crushed silicon particles during mild wear, and by subsurface cracking at silicon particles in the highly deformed wear zone during severe wear. The materials are commonly used for self-lubricating plain bearings or electrical contacts. They are proprietary materials owned by the Graphite Metallizing Corp. Graphite/metal alloys take advantage of graphite's special properties. It is compared to a deck of cards. Individual layers slide off the top surface easily. This phenomenon gives the material a self-lubricating ability found in no other material. Graphaloy's self-lubricating features mean the operator can eliminate grease or oil that normally evaporates, congeals, or solidifies, causing premature failure. The graphite matrix can be filled with a variety of impregnates to enhance chemical, mechanical and tribological properties. The material provides a constant, low coefficient of friction rather than just a surface layer, helping to protect against catastrophic failure. Lubrication is maintained even during linear motion, lubricant is not drawn out, and dust is not pulled in. Graphaloy wear components also improve reliability during low-speed operation, frequent starts and stops, and switchovers from standby to continuous running. Graphaloy bushings are available in more than 100 grades of material in any desired size or geometry, including cylindrical, with or without grooves, flange or double flange, split, and metal-backed. 2.3 Fabrication of Al-MMC, AL6061 plus vol. % of SiC and volume %gr, by stir casting. Aluminium Al6101 of commercial grade was used as the matrix material. SiC and graphite particles with size varying from 26 to 30 m was used as the reinforcement material. Table 1 displays the chemical composition of Al6101 used in this research work. An orthodox casting technique was used for the manufacturing of composites. Setup for stir casting technique is displayed in Fig. The proper amount of Al6101 was heated in a graphite crucible placed in an electric furnace. The graphite was also preheated to 720 C with the help of a separate electric furnace. After melting the Al6101 in the electric furnace, graphite reinforcement particles, preheated, were added and mixed. Molten mixture was stirred at 550 rpm for 10 minutes by using an electric motor which is fitted with a mechanical stirrer. The temperature was kept constant, 800 C, during whole stirring. The molten aluminium alloy split into droplets because of shear force imparted by the stirrer at the presence of graphite. Now the molten mixture was exiled from the graphite crucible into a permanent preheated, 500 C, steel mold. The molten mixture was allowed to solidify in steel mold. The casted composite was subjected to T6 heat treatment. Heat-treated composite was tested for various tests. The same procedure was followed to manufacture all other composition. The composites were manufactured at 3, 6, and 9 weight % of SiC and graphite reinforcement particles. The size of plate is 12 mm diameter x 700 mm. Experiment did pardoning of material on lathe machine. The final size of material is 12 x 30 mm. The pin was held against the counter face of a rotating disc, EN32 steel disc, with wear track diameter 80 mm. The pin was loaded against the disc through a dead weight loading system. The wear test for all specimens was conducted under the normal loads of 50N, 100N, 150N, 200N. The pin samples were 30 mm in length and 12 mm in diameter. The samples and wear track were cleaned with acetone and weighed, up to an accuracy of 0.0001 gm using microbalance, prior to and after each test. The wear rate was calculated from the height loss technique and expressed in terms of wear volume loss per unit sliding distance. In this study, pin-on-disc testing method was used for tribiological characterization. The test procedure is as follows. Run-in wear was performed in this stage. This stage avoids initial turbulent period associated with friction and wear curves. Final stage/third stage is the actual testing called constant/steady state wear. This stage is the dynamic competition between material transfer processes, transfer of material from pin onto the disc and formation of wear debris and their subsequent removal. Before the test, both the pin and disc were cleaned with ethanol-soaked cotton. c:/users/lenovo/desktop/1598514004239.jpg 3.3.1 Weight loss and wear loss. The alloy and composite samples are cleaned thoroughly with acetone. Each sample is then weighed using a digital balance having an accuracy of plus or minus 0.1 mg. After that, the sample is mounted on the pin holder of the tribometer ready for wear test. The specific wear rates of the materials were obtained by. The experimentation is performed on the N31 disc rotating at a maximum speed of 500, 1500 and 2000 rpm with the various loads of 50 N, 100 N, 150 N, and 200 N. The results we got from the experimentation is as plotted below in the form of table. 4. Experimental wear calculation. 4.1 Specific wear rate calculation. 4.1.2 Width, AL 88%, 66%, GR 6%. Variation of wear with load, N. 5.1 RSM Experimental design and analysis. Response surface methodology, RSM, also known as response surface modeling, is a technique to optimize the response, S, when two or more quantitative factors are involved. The dependent variables are known as responses, and the independent variables or factors are primarily known as the predictor variables in response surface methodology. While p-values are used for a particular point such as to test the hypothesis of whether the 70°F is the most comfortable temperature or not, the response surface is useful in determining a range of temperatures for the same comfort level. As maintaining the temperature exactly at a 70° could be very expensive, maintaining the temperatures within a range is often desired for cost-effective solution. Moreover, keeping very cool in summer or very hot in winter would be very wasteful. Response surface methodology, RSM, is very useful to optimize variables/factors more practically as compared to just the statistical significance test for a particular point. Point estimate is the statistical jargon. Minitab 19 software is used for RSM. 5.2 Components of experimental design. Consider the following diagram of a cake baking process. There are three aspects of the process that are analyzed by a designed experiment. Factors, or inputs to the process. Factors can be classified as either controllable or uncontrollable variables. In this case, the controllable factors are the ingredients for the cake and the oven that the cake is baked in. The controllable variables will be referred to throughout the material as factors. Note that the ingredients list was shortened for this example. There could be many other ingredients that have a significant bearing on the end result, oil, water, flavoring, etc. Likewise, there could be other types of factors, such as the mixing method or tools, the sequence of mixing, or even the people involved. People are generally considered a noise factor, see the glossary, an uncontrollable factor that causes variability under normal operating conditions, but we can control it during the experiment using blocking and randomization. Potential factors can be categorized using the fishbone chart, cause and effect diagram, available from the toolbox. Levels, or settings of each factor in the study. Examples include the oven temperature setting and the particular amounts of sugar, flour, and eggs chosen for evaluation. Response, or output of the experiment. In the case of cake baking, the taste, consistency, and appearance of the cake are measurable outcomes potentially influenced by the factors and their respective levels. Experimenters often desire to avoid optimizing the process for one response at the expense of another. For this reason, important outcomes are measured and analyzed to determine the factors and their settings that will provide the best overall outcome for the critical to quality characteristics, both measurable variables and assessable attributes. Unaffinitized topics. 5.3 Experimental result of wear test on AL 94%, SiC 3%, GR 3%, by using RSM methodology. 5.3.1 Response surface regression, wear, superscript 3/nm, versus load, N, speed, RPM, AL 94%, SiC 3%, GR 3%. Surface plot of wear, and number 179/nm, vs speed, RPM, load and NBSP, N. Graph 15, surface plot for wear versus speed, load, AL 82%, SiC 9%, GR 9%. Conclusion. 1. Aluminium alloy and its composite SiC, graphite have been effectively fabricated by stir casting method using two-step addition of particles in the melt. 2. AL 6061, SiC and graphite composites were shown uniform distribution of reinforcement particles in the base matrix material. 3. The wear resistance of Al6061 alloy increased after addition of SiC and graphite particle. The volumetric wear loss affected by load and sliding speed. 4. Wear loss decrease with increase in percentage of SiC and graphite composite, i.e. addition of SiC 9 vol% and Gr 9 vol% to Al6061 decrease the specific wear rate. 5. The hardness, ultimate tensile strength as well as percentage of elongation reduce with increase in SiC and graphite content. 6. Hardness increases with increase in Wt% of SiC and Gr. 7. Tensile strength, yield strength, and percent elongation increases with increase in Wt% of SiC and Gr up to 15%. 8. From the results, the use of steel particles as replacement of conventional reinforcements such as SiC and Gr in AMCs, has great promise for applications where high specific strength, toughness, and wear resistance are desired in service. 9. The hardness of the composites increased approximately by 15% with increase in steel particles from 3 to 9 weight% of SiC and Gr. Also, for the same range of steel concentration, the ultimate tensile strength increased with increase in steel weight% and were all higher than that of 9 weight% reinforced SiC and Gr. The specific strength and fracture toughness equally followed the same trend with respect to steel concentration, and comparison with SiC and Gr reinforced composite composition 1. Kenneth Kanayo Alanimi, Adidomalola Victoria Faye Jemison, Enthabisang Beauty Maladi development of aluminium-based composites reinforced with steel and graphite particles, structural, mechanical, and wear characterization. Received November 2, 2017. Accepted April 30, 2018. 2. Pardeep Sharma, Krishan Palawal, Ramesh Kumar Garg, Satpal Sharmak, Dinesh Kanjaja. A study on wear behavior of Al/6101/graphite composites, received October 13, 2016. Received in revised form December 22, 2016. Accepted December 26, 2016. Available online January 7, 2017. 3. Nagaril M1, Oradai, Parashivamurthy, and Korea comparative study on wear behavior of Al6061-6% SiC and Al6061 6% graphite composites, Nagaril, JAPPL Mekong 2016. 4. Sitabathula Madhusudan, Mohammed Mulana Mohudin Sarkar B, Narsapali Bhargavarama Mohan Rao Mechanical properties of aluminum copper, P. Composite metallic materials, 2016. 5. Navnath Samhaj Kalyankar, Rahul D. Shelke study of properties of Al-LM25/SiC metal matrix composite fabricated by using stir casting method. International Journal of Mechanical Engineering and Technology, IJERT, Volume 7, Issue 5, September-October 2016, pages 133-141, Article ID, IJMIT-07-05-016. 6. MD Habibur Ramana, H. M. Mamun Al-Rashid, Characterization of Silicon Carbide Reinforced Aluminum Matrix Composites 2013. 7. Pardeep Sharma, Dinesh Kanjaja, Satpal Sharma, Parametric Study of Dry Sliding Wear of Aluminium Metal Matrix Composites by Response Surface Methodology, 4th International Conference on Materials Processing and Characterization, 2015. 8. Vaini Kumara, Rahul Dev Guptab NK Batra Comparison of Mechanical Properties and Effect of Sliding Velocity on Wear Properties of Al6061, Mg 4%, Fly Ash and Al6061, Mg 4%, Graphite 4%, Fly Ash Hybrid Metal Matrix Composite. 3rd International Conference on Materials Processing and Characterization, ICM 2014. 9. S.C. Patnaik, P.K. Swain, P.K. Malik, SKSAH001 Wear Characteristics of Aluminium Graphite Composites Produced by Stir Casting Technique, ISSN, 2231-3818, online, ISSN, 2321-4236, print, Volume 4, Issue 3. 10. Ricardo Augusto Goncalves and Marcio Bachida Silva Influence of Copper Content on 6351 Aluminum Alloy Machinability. 11. R.L. Duas, C. Subramanian and J. M. Yelup Dry Sliding Wear of Aluminium Composites. A review, received February 25, 1996. Revised August 30, 1996. Accepted October 14, 1996. 12. M.S. Prabhudeva, V. Oradab, K. Venkateswarluk and H. Siddalingswamit and S. A. Corey Influence of CU Edition on Dry Sliding Wear Behavior of A356 Alloy. 12th Global Congress on Manufacturing and Management, 2014. 13. Mechanical Properties of Aluminium Metal Matrix Composites Under Impact Loading. Hamida and M.S.J. Hasherny. 14 Palani Sami Shan Magazundaram investigation on the wear behavior of eutectic LSI alloy Al2O3, graphite composites fabricated through squeeze casting. Received, December 7, 2013, revised, May 11, 2014. 15 Devarayu Aruri, Kumar Adipua, Kumarazwamy Adipub, Kodavirakari Bazaveda wear and mechanical properties of 6061T6 aluminum alloy surface hybrid composites, SiC and GR, and SiC plus Al2O3, fabricated by friction stir processing. 16 Michael Oluwatosin Badun Rina B, Kenneth Kanayo Alanimi, Leslie Heath Chown Aluminium Matrix Hybrid Composites, a review of reinforcement philosophies, mechanical, corrosion and tribological characteristics. Received September 6, 2014. Accepted May 5, 2015. Available online June 9, 2015. 17 Wear properties of brass samples subjected to constrained groove pressing process. M. Ibrahimi, S. H. Adarilar, F. Javan Rudi, C. God, H. S. Kim. 18 Adel Mahmood Hassan, Suleiman Z.S. Aldi. Improvement in the wear resistance of brass components by the ball burnishing process, received March 22, 1998. 19 Monica Wakoiza, Impact of oxidation of copper and its alloys in laboratory simulated conditions on their antimicrobial efficiency. 20 Mechanical properties of aluminium metal matrix composites under impact loading. 21 Leaching and recovery of zinc and copper from brass slag by sulfuric acid. I. M. Ahmed, A. A. Nail, J. A. Dowd. 22 Salima In, Nile Yuxel, Julia Dermu, Simj Jen Kalp, where behavior of Al/SiC/graphite and Al/Feb/graphite hybrid composites. 23 Z. B. Luklanska and J. E. Castle, microstructural study of initial corrosion product of aluminium brass alloy after exposure to natural seawater, 1983. 24. Performance of aluminium alloy graphite bearings in a diesel engine. B. P. Krishnan, N. Raman, K. Narayanaswamy and P. K. Rohatgit. 25 Hiroji Tokusu, friction and wear properties of aluminum particulate graphite composites, 1977. 26 Wear characteristics of metals. T.S. Air. 27 Fabrication methods used to prepare Al metal matrix composites. A review. Prem Shankar Sahu, R. Bench Hor.